we're about to learn a very fun way to solve matrices, solve a system of equations. And I guess it's what I consider a really fun way because it's like puzzles. It's like doing Sudoku or something. Now, sometimes students don't think of it that way and don't like it as much as I do, which I didn't understand until I started teaching because I always thought it was so fun. Anyway, what we're about to do is kind of like the elimination method, and because of that, there are certain rules we have to follow. Okay, here are 3 rules that we can follow for the example we're going to be doing here in a second. All right, so step 1, we can interchange, which that word means trade. So interchange or trade any 2 equations, which instead of calling them equations, now that we've written them in a matrix, we're going to call them rows. So the rows of our matrix are the equations, and we can trade any 2 rows. We can replace a row or an equation with a non-zero multiple of itself. And we can replace a row or an equation with itself added to another row plus a multiple of another row. So I don't know if you remember this from our quiz today. I'll look at it maybe in a second from our notes in section 6.2. But at one point I multiplied an equation by a 3 so that I had a 9, a positive 9, and a negative 9, so that when I added them together I got that variable to cancel out. That's kind of what these are saying. We can multiply any row equation, because a row is an equation, by a number, as long as it's not 0. We can't like multiply by 0 and turn everything into zeros and solve all the world's problems. That doesn't work. We can also add equations together, or rows is what we're going to be calling them. Add rows together to get new equations or new rows to work with. And the reason to do that would be to get rid, like we saw earlier from section 6.1.6.2. That would be used to help us cancel out a specific variable so that we can solve for a different variable, right? So we're trying to get some of those numbers in our matrix to turn into zeros. Because when the numbers in the matrix are 0, that means the coefficients of the variables are 0, which means we've canceled that variable out of that equation, so that we have fewer variables in the equations that allows us to find the answer that way. Okay, let's go step by step through an example here. Okay, use row operations to put augmented matrices in one of the following forms to help in solving a system of equations. So there's 2 different forms. There's one called row echelon form, and that's where we just get our upper triangular form that we saw at the very beginning. Okay, so here are some examples of problems that are in what we call row echelon form. So I'm just throwing in random numbers just to help you see the system. Sometimes I don't bother making that a dotted line. Drawing dots is annoying. I just put a line in that's not a bracket. That works fine. So this is in what we call row echelon form. Let's go through the characteristics and see why this is in row echelon form. So the first non-zero entry in each row is a 1, called the leading 1. So the first row starts with a 1 in the first column, and the second row starts with a 0. So the first non-zero number is in column 2, and it is a 1. The leading one of a given row must be to the right of the leading one of the row above it. So see how this leading one of our second row is to the right column of the leading one of the row above it. So you always put them in that order. any row of zeros cannot be placed above a row with non-zero entries. So if we end up at some point with an entire row of zeros, it has to go at the bottom. So here's another example of that, what that's saying. Like if I had something like this is just another just random example that's in row echelon form. So let's say everything zeroes out. So that happens when we have a dependent system. When we have infinite solutions, we can get a row that zeroes out, like we saw on the quiz today. So the row that zeroes out, that's infinite solutions. That's called consistent dependent, right? Again, that's stuff you will learn in section 6 too if you haven't done it yet. But see how our first row, the 1 is to the left of the second row, the 1 is right of the one above it, and the third row is a row of all zeros, and that goes at the bottom. So these are both in row echelon form. They are both following these rules. And the cool thing about row echelon form is it's like that upper triangular form. If this column represented x and this column represented y, then we would know that y equals 4, and therefore we could plug that in for y and find what x is. Just like we did in that very first example today, taking z and plugging it in, finding y, and then taking y and z and plugging them in to find x. That is why we like row echelon form, because it's like the upper triangular form. It allows us to find answers and plug them in easily. Okay, I know this one is weird. We'll learn more about that later. Okay, now reduced row echelon form is a little bit more painful to get to, but it's really cool when you have it done because your answers will just be done. The matrix is in row echelon form, just like we just learned about, but besides that, anything that's not a 1 or the constant is a 0. So in order for this to go from row echelon form to reduced row echelon form, we would have to somehow turn that 2 into a 0 so that it would look like this. So that we have a 1 and a 0 and then our constant, a 0 and a 1 and our constant. And what that does is these two numbers will be our answers. This will be x equals this number and y equals this number. Or here's our row echelon form for a 3 by 3. We would have 1, 0, 0, 0, 1, 0, 0, 0, 1. These numbers over here would be our solutions. X equals 1, y, or x equals this constant, y equals this constant, z equals this constant. So you can solve a system of equations by just putting it in row echelon form and then substituting. But if you go clear down to reduced row echelon form, then your answers are in the augmented part of your matrix. And you're done with the entire problem. Okay, so these little red things, the little red numbers, are telling us what order to get these numbers in. The very first thing we always want to do is get that 1 in the top left corner. The next thing we always want to do is get a 0 right below it. Then, if we're just working with a 2 by 2, we'll get the 1 in the bottom right, and then the 0 above that. If we're working with a 3 by 3, we would go ahead and get all of the 1 and the 2 zeros in the first column, and then the 1 and the 0 below it in the second column, and then we would get the 1 in the third column, and then we start working getting through these zeros. And the reason we do these in this order is it keeps us from undoing stuff we've already accomplished, so that we are not turning zeros we already turned into zeros into other numbers and messing up this form that we already had. So going in this order to find those, to get those 1s and 0s in the right places, makes it the easiest by going around like this, or in this case around like this. Okay, unless you've seen this before, at this point you're like, what in the world is she talking about? That's valid to not have any idea, but I feel like my video is already long enough with that confusing explanation, so I'm going to stop my video.